Rohit, you can start the recording if it's not
Yes.
okay. So if I'm audible clearly, we'll start now. Oh, good morning, everyone. Today's session is probably our final session of this summer school, which is on cosmology. This session is split in two parts. We'll have our first part today and the second part day after tomorrow. So before we start, I'll give a brief introduction of myself. I am Rishabh Srivastav. I am a final year student. I have completed my BTech in 2 weeks. So I did my BTech in metallurgical and material science, and my MTech or IEEE in data science. And now I'm going ahead to University of British Columbia. And with me, I have, oh yes, and I was a coordinator of Horizon in 2021 and yeah, Horizon head in 2022. Yeah, it's been quite a long time since then. And with me, I have yeah, Rohit and Amishi, both of whom are currently coordinators of Horizon. So it seems like we are good to start the session. So yeah, today we are gonna go through cosmology and we'll explore the unfolding of the universe. But before we do that, before we discuss about various aspects of cosmology, uh, a very simple question that I would like to ask this session to be as interactive as possible. Yeah, it should not be just like, I am speaking and you are the ones who are listening. So let's do one thing. I have my eyes on the chat box. However, yeah, I mean, if I ask any questions or if you have any doubt or if you want to discuss anything even in between the session, feel free to interrupt me and probably raise your hands. I think we have an option where we can allow you to speak. Whoever has raised their hands, or else yeah, chat box is there. But yeah, I mean, please keep it interactive. Otherwise, it will just get boring, and you might just even go and sleep. Okay. So, before starting any session on any topic, the first thing that we should usually ask, being scientists ourselves, is what does the topic mean? Just a minute. I hope my slide has has it? Can someone confirm? Okay. So my basic question is, we hear stuff like astronomy, we hear subjects like space science, cosmology, okay, and I'm getting more and more responses. Cosmology is universe in smooth or large scales? I'm assuming you're trying to say small or large scale. Kind of makes sense. That's what cosmology is. To all the people who are a bit confused, because I personally, when I started reading the definitions, I was a bit confused between all these terms. For some reason, they all seemed the same to me. But when I studied it, I actually realized that cosmology has a proper definition of its own, just like we have like other definitions. So As someone has already said it in the chat box, cosmology is study about, it's a, yeah, we can fairly say that it's a part of astronomy, and it's someone has said that they cannot see the chat box in the meeting. And I mean, yeah, right where you have written this message, I think that's what the chat box is. Yep, anyways. So what is cosmology? So in cosmology, we study about the universe as a whole. Astronomy is a very, I'll say a very wide field where we study about various, little aspects and the larger aspects of universe. We study about exoplanets, we study about stars, and as you might have seen in your last session or the session before that, uh, even like black holes are a part of it, the stuff that you learned in your last session. But when we are doing cosmology, we study about, the origin and evolution of universe. And yeah, we start from Big Bang and then we move on into the future. We ask questions like, I'm hoping all of you might have read the very famous Stephen Hawking's book, where he starts this book with these few questions that we all think some point in our lives, that where where did we come from, where we are heading to. While we did come from, I mean, we were always a part of our planet Earth. However, it's more about where this universe came from and where we are going. So we start from Big Bang and we see where this, future universe is heading. Are we going to just expanding? Is it gonna remain stationary? Is our universe stationary or is it expanding? There are lots of questions to it, and I'm pretty sure there are lots and lots of documentaries and videos on this. And I mean, if you guys are attending today's session, I'm assuming that you are already interested in already and might know a few stuff. What we will do today, we will go through the scientific study of cosmology. This session will involve, I mean, lots of equations. A part of it will start with very, very basics that we'll do today, but then we'll move very quickly to, some of the physics that is used to do cosmology, because cosmology is about astronomy, where we have facts, where we have data, where we analyze data, and when we find stuff. But cosmology is a lot more about the physics aspect of it. So yeah, but before continuing into cosmology, before starting the study of cosmology, we will define and we will see. I know you all know it very well, but yeah, it's important for us to. Okay, is there a problem in my voice? I know my slides are lagging for some reason, but okay, is it fine now? Oh no, no, I was not taking longer pauses of might be see the same thing again. There's nothing more I can do at this point, I think. Probably the internet issues. Anyways, yeah, let's continue. Slides are lagging for some reason. I don't know why. But yeah, I mean, I'll wait till you guys can see the slides before continuing. So, as we see in cosmology, we study about the origin, evolution, and fate of the universe, and we see the universe on a very large scale. But then, in astronomy, astronomy involves everything. starting from the dynamics of, very, very little celestial objects like planets, like stars, then we move on to galaxies. So in a way, astronomy covers the, the nature, and we try to explain the physics of it. So astrophysics is a, once we are clear about all these uh, uh, is my audio fine? Uh, it's breaking up a lot. Oh, just a minute, just a minute. Uh, can someone confirm if you can hear me, or is it still like lagging or me? Okay, 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 okay. Yes. I'll continue. And yeah, I'm really sorry. I just hope this wouldn't have been an issue, but unfortunately it is. And then just let me know. Just let me know. Uh, yeah, whatever happens. Yeah. So as you can see the definitions, this is what these three mean. So yeah, now if someone asks you, yeah, please do mention like the difference between cosmology, astronomy, and astrophysics. This is the least thing that I assume you will, take from this session. Oh, and yes, there's one more, small confusion that people usually have. Yeah, no, to you guys. Astrology. It has nothing to do with astronomy. It has nothing to do with, I mean, as far as I know, nothing to do with any science. And as you can see on your screen, it's, yeah, simply, I personally have no idea what it is. And yeah, I'll prefer that even, you guys just keep it a little bit, different from whatever we do. So moving on now, if since you guys have realized, we'll move on from these definitions, and we'll see the contents of our session. Someone has said it's pseudoscience. I don't know. I have no idea. And I mean, I've seen people, mentioning that, okay, you do as I'm like, sir, that's not what I do. Anyways, yeah, let's not hate something, and let's move on, and let's focus on cosmology, because that's what we are here for today. Uh, so this is how the flow of today's session will be. We will start from the cosmological principle, from which is like the very, very space time. From there, we'll discuss about something called as an FLRW metric. All of these in very detail. These are like the basics of what we do. So yeah, I mean, there aren't going to be too many equations today. We'll just, try to build your knowledge so that you can, do a little. So let's get started. Are you guys ready to actually? get into and to learn about what cosmology. Oh, is it like very low? Let me see. Can you guys not hear me? Okay, yeah, I'm sorry this keeps on happening like in between. Oh, yeah. And yeah, we'll just continue then. We'll start with our very first topic, which is the uh, cosmological principle. Now, to understand what principle means, we need to know about like two terms which we need to be very clear about. When I was studying, when I was a kid, like a few years ago, I used to get very, very, very confused about these two terms that you see on the screen right now, which is like isotropy and homogeneity. And it's imperative that we clearly understand what they mean. And the picture that you see on your screen can give you a fair idea. I just want to know if it's just me or even like you guys were ever confused, and do you guys listening if anyone? I hope my voice is not lagging now. Okay, okay. As Swastika has said, okay, so the question wasn't clear. So my question was, I was asking the difference between isotropy and homogeneity. For me, it seemed like, I mean, I used to get very confused about these two terms, but they are very different. In fact, it's the the combination of two that is actually involved in the cosmological principle. So that is why I just wanted to know if you guys ever felt the same. But yeah, as I see a few people have mentioned that it, they do not understand a very clear difference between the two. So yes, let's look into it. Imagine that you are standing at one place and you look around. You turn 360 degree and just you look around you look yeah around. So what isotropy means is if you look around, you see the same thing everywhere. As you can see on the left hand side on your screen, if someone is standing on the center of this board and if they just keep moving around, ignore the numbers that are mentioned on the board, but they will see the same thing, right? Yeah, that's what isotropy means. A very simple thing. Now then, what is homogeneity? Homogeneity simply means now for isotropy, you are standing at one place and moving around. But when it comes to homogeneity, it's about you moving at different places and still seeing the same thing. As you can see, in the figure on your right, even if you move a little bit to the left or right or anywhere, you will still see the same thing. Now, if you see I think it's a dartboard or yeah, whatever it is on the left side for isotropy. If you're standing at the center and if you just move around, you will see the same thing everywhere. But then if you move a little bit, upwards, a little bit downwards, you won't see the same thing again. So it won't be like isotropic, but then even it won't be homogeneous because you saw something different at the center and you saw something different at like some places. Similarly, now on the right hand side of your screen, the place where you are seeing the homogeneity thing, if you are standing like in one of the yellow circles or one of the sorry, not it's not yellow, I'm sorry, one of the blue circles or one of the blue sphere or whatever it is, and So you see a red one on all your four sides, but then if you like move around, you will see like blue ones on all your sides. So someone is asked, is it just a frame of reference difference? Uh, well, the point is if something is homogeneous, the frame of reference won't matter because you can just, move around and you will see the same thing. But then if it isn't, if it's inhomogeneous, then the moment when move around here and there, you will start seeing different things. So now hoping that you are clear about the difference and the meaning of isotropy and homogeneity, the cosmological principle simply says that our universe is both isotropic and homogeneous. It's a very simple line. Now, like, have you guys understood what we are trying to say? We are trying to say two things. We are trying to say that someone has raised their hands up, I guess. Okay, maybe not. I don't know. So I'll continue. We are trying to say two things here. We are trying to say that, you know, uh, if you stand at one place and if you look around the universe, you will see the same thing. And even if not just stand, and even if you move to different places, you will see the same thing. That's it. And yeah, just a minute. Okay. So now my question is, you do think about, I mean, yeah, do you agree to the cosmological principle? It's my, I have this question for you all. How many of you agree that cosmological principle is true? Well, so if we say that that is how our universe is governed, and if it is true, then you should be seeing the same thing, right? So, but then when you see it in your room, you talk about something being homogeneous. Then, like, if you see in front of yourself, there's something else. You might be having your laptop or computer screen, whatever it is, and then when you move around, you don't see it. It's not at all homogeneous, neither homogeneous nor isotropic. I mean, if it were, it would have been very, very, very boring. I don't know how I personally would have survived in a homogeneous and isotropic world. Okay, yeah, I see a few discussions about if it is on a large scale or if it depends where we are looking. Hold on to it. Hold on to your discussion. Yes, we'll see. Now, even if we zoom out a little bit, it's not just about our room. Even if we zoom out a little bit and if we see our colony or if we see a city, it's still not homogeneous or isotropic, right? Uh, facing major internet issues. Okay, yeah, it's there on my yeah, your screen now. Okay. And then even if we zoom out more, the countries are not homogeneous nor isotropic. I mean, you can clearly point out a world map where it's all different. You have India on one side. If you see towards, our east, you will see China and Japan, other countries. If you see on the west side is US. I know the earth is round, so I am not a supporter of flat earth. So yes, it's a bit unfair for me to say if we want to look at left or right. But yeah, I mean, you get the gist of what I'm trying to say. But further, even if you, like zoom out a little bit more, and if you look at solar system, even that is not homogeneous, nor is it isotropic. Milky Way, it still isn't. Now we have zoomed out a lot. Let us zoom out a lot. And we go to, something called as, distance of a few megaparsecs. it still doesn't seem homogeneous or isotropic. So, and one thing that I want to mention, someone has said that it depends upon where we are looking, and it's not even on a large scale can it be homogeneous. If it depends upon where we are looking, it cannot be called isotropic, right? Because that's what isotropic exactly means. Irrespective of where we are looking, it should be isotropic. Like it should look the same. So then, but we do still, I mean, it is called the cosmological principle, so it has some sense to it. It should be true, right? It. Uh, so this is where it happens. When someone can ask you this question, this is a very, very valid and a very basic question. At what scale is universe actually homogeneous and isotropic? On what scale is the cosmology that we do, is valid? Scale that we see is actually homogeneous and isotropic. And then why is it called cosmological principle? A principle should be valid everywhere. We never say in a cosmological principle statement that at a particular we the central part of our galaxy is isotropic, but it is not homogeneous. If it is homogeneous, then we know it's unfair to call it a central part of our galaxy. Homogeneous simply means that even if I move anywhere from a point where I am, it should be homogeneous. That is the meaning of homogeneous. Homogeneous simply talks about not being at a place and having the ability to move here and there and still, seeing the same thing. So it's unfair to mention a specific point as a special point in our universe, because that is what inhomogeneity simply is. Well, to all the physicists out there, I'll explain to you in a very, very mathematical term what homogeneity and isotropy is. So assume a vector R, normal vector R as a function of x, y, z. Now x, y, z are our coordinates. We'll see what coordinates and everything mean in detail in future, but I'm assuming that you have like some idea about what coordinate systems are. So and R is now when you have a vector R as a function of x, y, z, it is a normal random vector. If someone says that the vector R, a function of xyz, is not a function of xyz, that simply means that it is homogeneous. I mean, no matter what values xyz takes, the value of R is still the same. But remember that R is still a vector. So that's what homogeneity mean. Homogeneity means that it is independent of the coordinate system where we are. Now, the R vector, since it is a vector, it will have its own components, right? Yeah, the the vector is homogeneous, yes. Or fair to say the vector is homogeneous because the space where we are, it can have, I mean, depending on where it is, or even in a way that we can say that the space itself is homogeneous. I mean, there are two ways to describe it. Space being homogeneous simply means that no matter where you put the value of x, y, z, the vector R sees the same thing. So yeah. And what isotropy means is now it is a vector, so it will have a is your doubt clear before like I proceed? And we need to go very slowly and we need to clear our doubts for yeah, some it might get a little bit boring, just please hold on to it because we'll look into more detailed stuff in the next session. Today we'll cover very, very basics. Now, what does isotropy means in this sense is the vector R, it should, since it is a vector, it should have multiple components, I cap, j cap, k cap. The moment I say it is a vector R, its components are not different. It has yeah, in a way, it's not a vector anymore. It's a scalar because it's the same wherever we are. It does not change its values with direction. So that's what it means. Now, I hope you have understood the meaning of homogeneous or isotropic. We are talking about universe in general. The stuff, when we say universe is homogeneous and isotropic, we mean that turn around, you will see the same thing. And then this is true for every point in the universe. Or we can say that there is no single special point in a universe. As simple as that. Every point is the same. There is no center of the universe because yeah, very simple. There's no center of the universe. And then it looks the same everywhere where we go. That is what it means very simply. It's not about any particular property that is homogeneous. Universe is homogeneous and isotropic. So the space that in where we live in. Yeah. Are we like good to continue? Okay. Now, while we keep on saying this, do we have any proof? Uh, there are no points where there are like vacuum or there are no. Okay, matter is present at some points, vacuum is present at some points. But again, as I said, as you can see on your screen, that the cosmological principle is only true at the scale of 100 megaparsecs. So when you go at that scale, you suddenly you know lose this thing about difference of matter and vacuum at individual points. That is exactly what I'm trying to say. I mean, even if you look in your room, you won't call it. I mean, at some point you are sitting, at some point there might be your bottle, at some point there might be a computer screen. It is not at all homogeneous. And even if, as we just saw, even if you are at a solar system level, it's not homogeneous, neither isotropic. So at some scales, even if you go to 100 parsec, like 10 parsec or 1 parsec scale, then you will not find it homogeneous and isotropic. But then as we zoom out at the scale of 100 megaparsec, that's what we see. We see that it is, I mean, yeah, we have not zoomed out that much. So we need a proof of this. And as someone has said, that is the proof that we have. The WMAP survey that was did way back to point out the cosmic microwave background showed something very interesting. I don't think the slide has changed. I'm trying to show you the CMB map. Oh, no, 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 that's not what I'm trying to show. Uh, I have switched on to a different slide. Do I have to wait for it to change? It's very irritating, this lag. Mm, it is still lagging this. Okay, let's do one thing. Amishi, can you present? Or like any of you guys present? I'll just speak. Maybe, that will clear out at least the presentation lag. I'll just stop sharing and I'll stop sharing. Yeah, I'm sorry guys for the delay. I think it will be better if someone else shares so that I can just keep on speaking. And if I don't share, probably my voice will be better too. Just a minute. Meanwhile, if you have any doubts, please ask. Please just go ahead and ask. And I apologize for the delay again, like for the problems. It's all technical. No doubt, sir. Why universe can't have center? It's simply because it doesn't. I mean, what how we do science is we have things. Science is all about trying to understand how things are and why things are in a certain way. So that's how it is, and that's what the cosmological principle means. Ki there is no center of the universe. Like there's no reason to it. Yes, yes, we will go to it. We'll go to it. You guys are giving spoilers, so we will discuss about it. About the anisotropies in CMB map. Good question. Good question. How do we know that it looks like this at 100 megaparsecs? And someone has answered it. It is because of CMB. Yeah, you are right. But then there is something that I mean, as you have said that universe was concentrated at a single point, so it does not have a pinpoint center. But when it was expanding, something happened, something called as inflation, due to which little these inhomogeneities happen. That is the reason why you and me exist today. That is the reason why you at smaller scales we do see certain differences. So, but yes, so. When someone is asked, let me read the question. When you say that at large scale of 100 megapascal, the universe is homogeneous, what difference has been created in measurement that made it possible to say it is isotopic homogeneous in large scales? How are you even going to large scale measurement? Can you please clarify? Yep, sure. So that is how we explain it. Now, you know, the cosmic microwave background is the answer. So when Penzias and Wilson, you might already know about the history of cosmic microwave background. When they were, I think they were trying to measure some frequency, not really microwave, or was it microwave? Something was there. Then they discovered these radiations coming from all parts of the universe, and it looked very, very, very similar wherever from wherever they were measuring it from. That is the reason it is called as background. And this something which is directly in support of the in support of the cosmological principles that at such large scales, like 100 megaparsecs is a very big scale. It is the scale of the universe. It is the scale at which we can see universe, very, 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 very minor details of it. So I hope that's what you are trying to ask. We will cover. Just have some patience. We will cover. And now, since I don't have to, bear the fate of showing my slides, I hope my then like we'll just continue. We will cover everything. But then yes, so this is the cosmological support of cosmological principle. But then again, as someone was did say in the chat before, and I would like to mention this again, that you can still see very, very little bit of inhomogeneity in this map. This map does not have one single color, right? Then but then our point is that these inhomogeneities, there's a temperature map of cosmic microwave background which actually shows all the inhomogeneities in it. It is not exactly a black body radiation, but then this homogeneity is very, 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 very small. So if it is like that small, so we kind of assume it to be true. So what we are trying to do here is at such large scales, we are trying to, just say that the cosmological principle is a fairly good approximation so that we can do cosmology. At every stage of physics, we live in a model-based universe. So we have to define our model in some way. So, approximations or hypothesis is somewhere where we, always start. And yeah, That is where we always start. So for doing cosmology, this is our approximation. So cosmological principle in a way is a reality at that scales, but you can, call it a hypothesis from where we start. A few questions that I see here are, does this map take account of dark stuff? Well, this map only takes account of, it doesn't even take account of matter, it just takes account of radiation. You know why? Because these radiations are coming from very early universe, when matter and radiation used to interact with each other very well, and the dark stuff that you are talking about, I mean, it has always been there, but its proportion was very, very, very less. So in one way, no, but then, yeah, in other way, probably yes. Okay, let's now continue. Enough of the cosmological principle. We spent a lot of time on it. Okay, I was trying to change slides for some reason. I'm sorry. Mishi is changed slide. Yeah, a little bit about now when we have talked about 100 megaparsecs, but then it is also very important to know and understand. Just a minute. Yeah, I am audible, right? Yeah, okay, okay. Yes, continue. It's also very important to understand various units that we use in cosmology, because we do not use a kilometer and stuff, because I mean you can assume that the kilometer is too small a unit for at such large scales. I mean, yeah, yeah, you can change the slide. Okay, so the very first unit that even historically this unit was I think used before parsecs and stuff, was the astronomical unit. And astronomical, the definition of astronomical unit is a little bit vague, I would say. It was defined as the simply as the distance between Earth and the Sun. I mean, initially, when it was thought that the distance is usually, I mean, the same only, but then again, we know that our orbits are not exactly circular. It is a bit elliptical. Although the eccentricity is very less, it is still elliptical. So then it was defined as the average distance between the sun and the earth. Now, astronomical unit is a very interesting distance. While it seems like it is, fine, but the scale where we are talking about, I don't think we can, just keep on continuing with this particular unit of distance. So, yeah, you can change, switch the slide. Now we come to the definition of a light year, which is a very, very common definition, and I'm pretty sure most of you already know about it. It simply means the time taken by light to travel. Why am I calling it time? It simply means the distance traveled by light in 1 year. And I'm hoping that no one has like any doubt in these two definitions. Right. Okay. When I say, I have a question. When I say that it's like the time taken, the distance covered by light in 1 year is how I define as light year. Is this definition accurate? Or am I missing out on some point? It's very important to, have your definitions very clear. Otherwise, I mean, you could land into big, big, big trouble if you want to do physics. Yeah, yes, exactly. That's the point which I missed. The although it is about the distance light travels in 1 year, it is more about the distance light travels in vacuum. Although we take it for granted because universe at that scale and even at any scale, universe in general is in vacuum. I mean, atmosphere is only present on planets and certain atmosphere on stars and stuff, but it is in vacuum, so we take it for granted. But then if someone is asking you for definition, please don't forget to mention this point that it is only true for uh, like in vacuum. Okay, now switching on to the definition that we are using here, the 100 megaparsecs one. And yeah, that is how we define a parsec. We do, we are talking about megaparsecs here, but yeah, this is the definition of parsec, defined as the distance at which the average radius of Earth, subtends an angle of 1 arc second. As you can see it on your screen, the diagram can help you imagine what that is. I mean, for me personally, the diagrams are very, very, very helpful. Otherwise, it gets a bit difficult. Someone has asked, how can space be vacuum? Because it has dust and other particles. Okay, so space does not have dust and other particles. It is the universe that has dust and particles. Space is the background in which dust and particles are present. So space is vacuum. Like Earth is also a part of universe. So it's not vacuum would simply mean that there's nothing in the universe. So that's why we call space as vacuum. Is it clear? Okay. Yeah, that is what parsec means. And then you can just, if you still haven't understood it, you can just read about it on Wikipedia. It's a very simple definition of a metric. But for people who have not understood it, you can just assume for now that it is a distance, which is approximately equal to 3.26 light years. And we are dealing in the scale of 100 parsecs. So you might have many doubts if you think about whatever we are going to learn going ahead. But then just keep in mind of the approximation. Whatever questions you ask, whatever doubts you have, just keep in mind that the hypothesis we are using of the cosmological principle is true. And then think about the doubts that you have if they still remain a doubt. We can surely discuss about it more, but yeah, just keep in mind this when we continue. You can change the slide. Okay, and now before going ahead and looking into the details, it's very important to understand what coordinate systems mean. And how do we describe space? As someone has just asked a question, this is a perfect time to discuss about what space means. Mathematically, we start our discussion with talking about multiple something called as coordinate systems. Now, what are coordinate systems? Are coordinate systems something real, or are they just a construction, of ourselves? In real world, there are no coordinate systems. We have a space, we have a region. I mean, we have this huge space, or we have, our own small room or anything. We have constructed this the coordinate systems just to, make things easier for us and for everyone else in order to describe, some things. A very, very simple example of a coordinate system is our Earth. I mean, whenever we mention about, let's go to this place, we mention in terms of its latitude and longitude, because we all agree to this coordinate system. So the first thing is defining a coordinate system, and the second thing is agreeing. Once we do that, it becomes very easy to tell someone that what your address is. We start with, 1D space, a very simple 1D space. Okay, be very, just listen to me very clearly when I use the word space and when I use the word coordinate. Don't mix these two. A 1D space is a space where one can only move in like one direction, I mean forward and backward. And how do we define, do you know of a coordinate system in 1D? A very famous coordinate system that we have been using right since, when we were kids, when we started doing basic maths. Exactly, that's the number line, which we have all. I mean, I don't know, for some reason, as we move on, as we study more and more, we do forget about a number line. But that is our 1D coordinate system. And then how we study about, I mean, obviously our space is not 1D, right? It's a different thing that it is 3D, but then whatever we look at our screens or we look at a paper, if we draw something, we talk about, our 2D space. How do we describe a 2D space? A very simple way to describe a 2D space is the Cartesian coordinate system introduced by Rene Descartes, and something that we all know very well. It is this matrix that we have, and we define a point which we take as origin, and then we move along x-axis and y-axis, and then corresponding to this space we have vectors. As in I cap, j cap, k cap, and then It's like very simple to describe what 2D coordinate system, Cartesian coordinate system in 2D is. But then that's not the only coordinate system, right? I mean, please keep in mind whenever we are discussing this, I have not introduced anything called as a curvature or a curved space. I'm still talking about a flat space. In a flat space, I am still describing a 2D like system in Cartesian. But as I said, we have more coordinate systems. The space still remains the same, but we have a 2D polar. Like we all have studied about it. Like we talk it in terms of r and theta. It also describes the same space in a bit different way. The coordinates are different. And if this is clear, now this might seem like a very obvious thing, which I'm just repeating again and again. But then just keep in mind as we move along, because the things I'm going to discuss in future, it might cause a big confusion to you guys. Similarly, we have 3D space where we add an additional coordinate in terms of Cartesian. With x and y, we add a z as well. You are free to choose which direction you want to choose as x, y, z. Just let me know, or let anyone else knows who is looking at looking somewhere. And then corresponding to polar coordinates, we have spherical polar coordinates and we have cylindrical polar coordinates. Because I mean, why not? We live in a world where it's easier to describe certain objects in that way. But then just again keep in mind that we are still describing a flat space. We are not describing a curved space yet. Spaces and these are different. I'm not saying that we cannot define curved spaces using any of the coordinate systems that we have measured. We can surely describe any space using all the systems, but it is just that it is easier. Certain spaces are described in a more easier way in certain coordinate systems. But then do we live in just a 3D space? We used to believe that we do, but something happened in 1905 that made us believe otherwise, which we will see as we proceed. But for now, we introduce another coordinate, which is time. And that is what we live in. We live in a four-dimensional space-time rather than just a 3D space. Because space is still 3D, but space cannot be differentiated with time. And more so when we are at, such large scales. Yeah, don't switch yet. I'll let you know when to switch the slides. When we are at such large scales, we have to take in time as a individual coordinate. It might not be necessary at this scale, because it's very interesting when I'm talking to you, and if you are at a little bit distant to me, you are not listening to me what I'm saying like right now at the moment, because the idea, the concept of homogeneity, the I'm sorry, not homogeneity, simultaneity is lost. We'll discuss about all these things as we just move ahead. Someone is it because whatever we see, it is because of light? Light has some finite time. It is because everything that we see around has finite speed. It is simply because of that. If I am saying that you are sitting somewhere, like hundreds of kilometers away from me, you are listening to me, but then you are not listening to me at the moment when I am speaking something. It takes time, between when I speak something and my audio is converted to an EM wave which travels to you via some route and then it reaches you. There's still some delay. So in a way, time and distance are related. That's how it shows you that how these two are related. And that is how when you get to know that, okay, we have to combine space and time to make it a new coordinate itself. We cannot leave. It's not independent. Time is not independent to space. And it is a very basic idea when you think about it, but it's simply that people didn't until 1905, until they're like very recent. So yes, and we'll see as we move along. Now you can switch the move to the next slide. Yes, Swastika, time is not a spatial coordinate. So that is why when we define coordinate, we don't call it time. We define it in CT. Just to maintain. I mean, you can leave it as T itself still, but then it is usually defined as C into T, so that we convert it into a something spatial. And then C is a constant. So yes, that's how it works. Now, before that, we need to understand the fabric of space-time. What space-time actually is. And I think we have had a fair discussion about what space-time is uh, till now. And I just want to mention one extra point here is that please remove all the idea of curvature and flatness of space-time and everything. We will go to it probably in just the next slide. But then for now, we have just discussed coordinate systems and we have just introduced various coordinates. We have not talked about space at all. Now, what is space? Space for now is just a four-dimensional continuum. How do you understand space? I don't know who said it, but someone very famous, describes space in a very simple manner. Just take this universe and remove everything that you know from this. Whatever's left is the space-time that we are living in. Very simple definition. And now once we know what space is, once we know what flatness is, yeah, you can move to the next slide. There's something very, very interesting. Now, how do you know that the space where you are, and how do you, describe a coordinate system? And how do you differentiate between coordinate systems? I mean, how do I say that I'm using a coordinate system of, let's say, Cartesian, or if I'm using a coordinate system of spherical polar? And even if I move a level above that, you might have a fair idea of what curvature means, but we'll go into it in future, like today only, but like in some point. But then just to mention that, how do you know that the universe in which we live in, if it is flat or if it is curved? How do we describe the space time in which we are living in? And I just want your opinions, and if you have read about it, it's good, but I prefer answers from people who have not read about it, because I just want people to think. So I just let you think and just answer. Just don't take much time, because we have lost a bit of time in those technical issues that we had in the beginning. Just think about it. How do we describe uh, critical density? We are not talking about matter here. We are not talking about any properties. We are simply talking about space. Space does not have any object. As I said before, space is something without any object. So, like, how do you, just mathematically be a mathematician here and think about it? How do you describe that something is something is curved, something is flat? Maybe looking at horizon. Do you mean the horizon of the universe itself? How do you look at, all you see is your horizon of the observable universe. It's an interesting thought. I agree. You can look at Earth's, horizon, and that's how you say that Earth is not flat and Earth is curved. But we are talking about universe completely. We're talking about, in fact, not about universe. We are talking about space. Please keep in mind that we are not talking about the universe. So we are not talking about any matter. We are talking about space itself. So when we talk about space, we are removing everything else from it. It becomes a question of philosophy. Where is, like, space there? But as a mathematician, what we do is we work in abstract spaces. We construct we make constructions, and that's how we define. I've given you some idea of how it is, but then just keep thinking about it. We will go to it like later on. Very good idea to know something about it is gravity. These are all causes that we will study in relativity. I'm not talking about any of these. I'm just talking about space and how do you construct something to describe about if something is curved or not. It is a very simple question. It has nothing to do with what is present in space. Assume a vacuum space completely, and then as a mathematician, can you do something to find out? Uh, but then yes, currently we need to know what it means. A very simple definition of an Euclidean distance. Euclidean distance depends upon a coordinate system that we are in. So this metric becomes very, very, very important to describe a coordinate system itself. Okay, you guys are going way ahead with Friedman equations and stuff like that. We are just talking about simple maths. If you actually just think, from your primary school studies, you will get the answer. So it's okay. If they satisfy Euclidean distance is, I mean, not some, it's not a relation. It's something, it's just how you define a distance. So Pythagoras theorem. Well, I don't know if I should call it if your answer is closer, but just keep in your mind. We'll discuss it. We'll discuss this. Now Euclidean distance ka definition we all know, and it simply tells you the difference distance between 2 points in a coordinate system, and this becomes very important because as we move along, we will see that in different coordinate systems, we describe it in different ways. So our definition of describing distances change. But then that is what we will use. We will use the characteristic of a distance to describe a particular coordinate system. That will tell you that what coordinate systems we are working in. And that is what we call as metric. You can move to the next slide. Yes, so we know a Euclidean system, but now we need to think about how do we find distances in random coordinate systems, because our coordinate systems need not be. I mean, the Euclidean distance is usually using Cartesian, but our coordinate system need not be Cartesian, right? It can be anything to describe any form of space, by the way, flat, curved, anything. But yeah. So as you can see, in very simple coordinate systems, we describe distances using dr square plus r square d phi, 2D polar, Cartesian, and 3D spherical polar. So, and the ds square that you said, the square of the distance, it's not a distance actually. Well, yeah, it's fair to call it a distance at this point. Ds square. It's this infinitesimal distance that we are concerned about. That distance, why is this distance very important? As you move ahead, and if you study like physics properly, you will learn about something. If you study field theory in future, you will learn about something that some covariant quantities, some invariant quantities. So ds square is something which is invariant. I mean, you'll learn about it. I'm not going to cover it here because it's just way too much physics. I'm telling you honestly, it is a part of a course that we have in IITM, and that course goes for over one semester. So it's difficult to cover one semester in just 1 more hour. By the way, we might have to extend a little bit. I'll try not to, but we might have to. But still, it's okay, like with doubts and stuff. But we have seen how 2D polar, 2D Cartesian, and 3D spherical is. Now we have to. I mean, now as we saw, our world is not the 2D or 3D. We live in a 4-dimensional space-time. So Minkowski introduced this 4-dimensional space-time, which is known as Minkowski metric. Now you can move to the next slide, where Minkowski is just an extension of our 3-dimensional Cartesian to 4-dimensional space-time, where as I was telling someone that it is not the time is not the only coordinate that we use. It is actually the CT. So when we talk about infinitesimal, okay, so please listen to what the terms that I am using very carefully. I am not going to use the term distance here. From here on, I will call it an interval. Because in 4-dimensional space-time, when you talk about 2 points, you don't talk about like uh, 2 points as such. You talk about 2 events, because time is one of the coordinates. So the term we will use is interval, and this is how this interval is measured. All the dx square, y square, z square, and then we have minus c square dt square. And yeah, here you will see, I mean, you might have a fair idea of what a metric tensor means, because you did see Schwarzschild tensor in. I hope all of you guys attended that session. I mean, yeah, here we'll start from the very basics. If some of you might not have got very basic idea what it means. No, this definition is very important and will come very handy when we see in future, in not a few minutes, but in some time, maybe in half an hour or so. Metric tensor. What does a metric tensor mean? Metric tensor simply means that okay, I'll describe it to you here. It's a bit easier for you to understand what it means. So we write interval in a particular coordinate system for a particular form of space-time. Like here, Minkowski is for flat space-time. Last year, I mean, last time you saw Schwarzschild, which was not a flat space-time. it was a part of space-time in a spherical symmetric system. But we are considering Minkowski here. How do we create this metric tensor? So as you can see, the eta alpha beta metric tensor, it has like 4 rows and 4 columns. So assume each row and each column to be representing one coordinate system. So the 0, 0 element of the Minkowski metric system is -1. Why is it -1? It is because it is the coefficient. Yeah, listen to me very carefully. It is the coefficient of the TT part of ds square. Now ds square in this case just has dt square, dx square, dy square, dz square. But are these the only terms that can be present? Can we have additional terms in our definition of ds square or our definition of line element or of interval? Whatever you want, you can call it anything that you want. I want an answer here. Are these the only terms that can be present, or can there be any additional terms? I'm not talking about flat spacetime here. I'm talking about in general spacetime. Consider TT as T in the TT term, not the constants. Constants are fine. Let's ignore the constants. Constants are they can surely be there. I'm saying, can there be more additive terms to ds square? Constants are just multiplied to these terms. dt square represents tt, the tt part of spacetime. Dx square represents the x time, yy represents ea. Yeah, exactly. As Aniket mentioned, there could be cross terms as well. We can have dx dy, dy dz, dz like dx, or you can even cross it with time. I mean, a very, very general line element, Minkowski element has all these terms present. But then how do you explain it is a bit difficult. That is why because we have started from Euclidean distance, right? Definition of Euclidean distance. So it's very simple that, we mention a z square there. So it's very simple that we call it ds square, dx square, dy square, dz square. But in a general coordinate metric, it can have additional terms. I want to ask you something. I mean, I'm hoping that most of you have attended the last week's session. Can you tell me something that you learned about where cross terms were also present? You did learn about something in last week's session on black holes, in the black hole physics session, where cross terms were present. There was this one topic where there were cross terms. You did see it. It's not the first time that I'm telling you this. Come on, come on, come on. I want answers now. Do you guys remember? Okay, no responses yet. Uh, well, I am disappointed. Anyways, I was expecting you to remember whatever you study. So yeah, it's okay. I just hope you don't forget whatever I am teaching you. I put in a lot of effort in this. Uh, do you remember learning about something called as a Kerr black hole? Anyone? KERR Kerr black hole. If you remember carefully, its metric was very complicated, but there was a cross term present in it. Do you know the reason of cross term? Because the black hole was rotating, so it became inhomogeneous. That's why we needed to have a cross term in it. So yes, there could be cross terms. And yeah, now moving ahead from Minkowski. Minkowski is not the metric that we use. Minkowski metric is actually used in an empty space time. Is it fair to say empty space time? Not an empty space time, but yeah, I mean a flat space time. That is why we use Minkowski in special relativity. But yeah, a flat and stationary, something another interesting thing about space time. Yeah, we can move to the next slide. Now coming to something that we have been talking about a lot, curvature. And how do we define it? because we have been talking about flat space, curved space, and a lot of, all these different things. And now comes the question that I asked you before. Because now this is where you will have to answer. What is there something that you can construct to, you know, tell them me that, I mean, the space time in which you are living in is curved or flat? Firstly, you have to understand what curved and what flat means. I'm not talking about our Earth, which you can fairly see that it is curved, because Earth is an object, and you can have, observables on Earth. Observable as in, you can like see stuff, you can see the sun rising, sun setting, and other stuff about it. But here we are talking about just space time itself. We are not talking about any particular object. So how do we describe curvature? How do you describe curvature? This is the question that I asked before. Now this is where physicist, loses his mind. An astronomer has lost his mind, way before, way long ago. This is where mathematician comes in. Mathematics is like the purest physics can get. Something that we need to construct. So you might have had some idea about, some of you might have no idea. I was gonna ask you your thoughts on it. You can still mention your thoughts, whatever you have in mind, but then you have some hint from the answer that you see on your screen. Anything that like uh, geodesics and stuff, we will go to it. We will go to it. It's geodesic. For now, you can just assume geodesic simply means the, the shortest distance between 2 points for now. In a flat space, sure, it means a straight line between 2 points. Yes, that's what a geodesic means. Or a very simple way to describe geodesic is, if you leave an object at one point, how does it move in space time if it is not being acted upon by any force? That is what geodesic means. This is a general definition. Now, how does it, what it specifically means? How does it change with time? We'll see, like as we move ahead. So for now, curvature, we have talked about, yes, curvature. How do we describe it? Someone has said a very, very simple way. We have learned about something called as triangle, angles and property of a triangle in our very, very basic studies that we have done, right? All the three angles add up to 180 degrees. Yeah, as physicists, we do not use the term degrees. We talk in radians. So yeah, pi. We know that, we have taken this for granted that it is simply, pi, the angles and property of a triangle. But then if you look at the Earth's surface, and if you see all these, latitudes and longitudes, you can choose any 3 points, choose 2 points on equator, any 2 points on your equator, and choose a point on your North Pole. It forms a triangle, right? Is it, do you guys agree? It still forms a triangle. A triangle is any object that is formed by connecting 3 points. And like obviously, well, yeah, 3 points. So it does form a triangle, right? But then if you see every latitude, when it crosses the equator, it is at 90 degrees. And then if you have chosen two latitudes which are, like 90 degrees across each other, then the angle at the North Pole is also 90 degrees. So technically, this particular the angle sum of this particular triangle is 270 degrees. So whatever we have learned in our, childhood is not completely true. It is only true for a flat space. That is a fair approximation, to be honest. But yep, you can move to the next slide. Yes. So as I was saying, the flat space has zero curvature. ABC, it just adds up to pi. And as we all know about. And yeah, as someone was asking about your geodesic, in this case, in a flat space, a geodesic is a straight line. A geodesic is simply, as I said again, the path an object will take if not acted upon by any force in a particular, like space time or whatever. You can move to the next slide. Now here we have something different, a hyperbolic space. The interesting thing about a hyperbolic space is that yes, one reason for it is the simplest shape, and the second reason for it is that angle sum property is something which is defined very clearly for a triangle. You might ask me why not for a quadrilateral or for a higher object of, I mean, for object of more number of points. It is because that object can be convex or concave. Quadrilateral, you can draw a convex quadrilateral as well, and suddenly your idea of angle sum will be lost, isn't it? Do you guys know that the convex and concave shapes, right? The square and parallelogram and all that stuff that we see, they are all are they called concave or convex? I mean, I forgot the difference between the two, but yeah, and the point is for them, it is all the angles add up to 360 degrees, but it is not true if you draw something like in which one of your points go a bit inwards, so that one of the interior angles actually exceeds even 180 degrees. So did you get your answer, Swastika? Okay. Yeah, that is the reason why we use triangles. Now, yeah, coming to hyperbolic space. Hyperbolic space is a very simple size. You might have seen hyperbolic space. Can you give me one example of an object that has curvature like the hyperbolic space that you are seeing on your screen? One real life object. Potato chip is not exactly hyperbolic. Yeah, it is the saddle which is actually hyperbolic. Potato chip actually is made in a shape so that it does not break. It is not hyperbolic. It has a name, that shape. I don't remember that name, but yeah. So yeah, the saddle is actually a hyperbolic shape. And now, what is the angle sum property for a saddle now? It or for a hyperbolic shape? It is a plus b plus c is not pi. It is less than pi. Pi minus a by r square. What is a? A is the area of the triangle that you are drawing, and r square is the something interesting. R square is the radius of curvature. If something is curved, it is bound to have a radius of curvature. Uh, yeah, and then it hyperbolic curve is also known as negative curvature. And yeah, this is how you define it. Just keep in mind this thing. And something, if you do, the radius of curvature for a flat space? Any ideas about this? Is it zero or is it infinite? It is actually infinite. It's not zero. And it's not tending to infinity, by the way. When we talk about exactly flat space, we don't actually define radius of curvature. But if you have to define it, you will call it infinity. If something like infinity actually exists. So as we move towards more and more flat space from a curved space, it tends towards infinity. And you can very well see this in this definition of a sphere. I mean, okay, right now we are seeing spherical space. If you put r to infinity, ABC becomes equal to pi. So yes, now as we are seeing a spherical space is the other kind of space. So we have flat space, or it is either positively curved or negatively curved. Negatively curved looks like what you have seen in your previous slide, and this is the how positively curved space looks like. Its angle more than pi, and that is how it is yeah, defined. These are only three kinds of spaces that are present. Now you can have more curvature to it, you can have more varieties to it, but that is how it is usually defined. I mean, you can even have, your radius of curvature not being a constant. There can be many variety to it, but these are the only three, like higher definitions of curvature. And I hope for now everyone has understood what curvature means. When we talk about curvature from now on, we talk about curvature of space time and not curvature of a particular object. When we saw a black hole in the last session, we usually mention something like, light though doesn't come out of a black hole. What that actually means is a light does not really know what a black, like it is in a black hole or something. The curvature at black hole is infinite. So when something is traveling through a curved space, it is bound to take a curved path. This is where your definition of this thing, geodesic comes in. As someone was asking me if geodesic is a straight line, it is a straight line in a flat space. But if you are on a curved space, your geodesic no longer remains a straight line. I mean, it's very simple. If you leave an object and if it moves, it will move in a curved shape, right? That will be geodesic for that particular object. It is not because it is acted upon by any force. It is simply because that is how the space is, and you have to move in space. You have no other option. How I like to explain it is in a very simple way. If you're walking through a road, if the road is straight, you will walk straight. If you are confined to walk in a road, which you technically aren't, I mean, people do go, sideways and you do anything that you want, but yeah. But if the road is curved, you have to walk in that curved path. That is like your geodesic at that point. Now you can get confused thinking in a way that your force is acting on you and it is keeping you on road. You are being constrained to stay there. This is where actually general relativity comes into play, which we will see into later. How the idea of gravity as a force is discarded in a way. Anyways, we'll go to it later on. You can change your slides. Yes. Now, point is how we have Swastika, I have forgotten actually the difference between convex and concave. I need to look into it. You can look into it, Google it, and I look into it as well after the session. I'll let you know. I have forgotten this definition of convex and concave for some reason. I'm really, really sorry for that. Yes. Now, what we need to do is we need to have a single particular definition in order to describe every space, right? It's a bit difficult if we have three different definitions, because depending upon what space we get, we'll have to keep changing stuff again and again and again. So, how we define, the triangle sum property in a very general space is we need to have something very generic. This is how you do physics. You define something, you look at certain individual properties, but then you need to have a general definition which involves everything. So that is how we define it. Pi plus kappa a by r square. Kappa is something which determines your curvature. As you can see, it is 0 for a flat space because it is just pi in that case, and then +1 -1 for as you move ahead. By the way, in certain books, they remove the term r square and they define curvature as kappa is equal to, your curvature constant divided by r square. So in that case, if you see your curvature won't be 1 or 0 or -1, it will have a certain value. You might see it like 0.2, 0.3, depending upon the value of r. This is how they do it in certain books, and we might also use it as we go ahead. Okay, you can switch the slide. And yeah, this is the overview of what we have looked into till now. And I hope by this your idea of a curvature is very clear. And please notice that we have not spoken anything about any something present in space-time. We have not talking about any object, any vacuum density or anything that you guys were mentioning earlier. We are just talking about purely on space terms. We're not saying that this is how our universe is, which is we are just talking about some abstract spaces. This is how it looks like. As we move ahead, we will try to see if any of these describe our universe, or if our universe is described in a very different way or something of that sort. You can just move ahead. Amish, you can switch to the next slide. Okay. This is where we are going to stay for a little while. The Friedman, Lemaitre, Robertson, Walker metric, the FLRW metric, because this is actually how how the physics of cosmology is done. Since we have, and my purpose of covering all the coordinate systems, describing all the Euclidean distances, describing everything that I did to get to this particular point. Before doing FLRW metric, I want to mention one thing. So we saw how we describe space-time. We saw how we describe Minkowski space-time in Cartesian coordinates. I mean, okay, Minkowski is itself Cartesian, so it's wrong for me to say that. But we saw it how we write it as minus c square dt square plus dx square plus dy square plus dz square. Now I'm keeping the space as same. The space is still flat, but then I want system. The coordinate system which I am using, which is usually uses r theta phi coordinate system, or the spherical polar coordinates. How do we describe it? You might have learned it. It is there in physics 101 that they teach you this. How do we describe Euclidean distance or just distances in spherical polar coordinates? Can someone just answer? I think it's you can type it, but one can unmute and speak as well. My question is, if it's not clear, how do you describe the distance between 2 points or in spherical polar coordinates? If anyone knows about it. What is the this mathematical, equation or the mathematical definition of a distance? Like for example, for Cartesian, it was dx square plus dy square plus dz square. What is it in case of spherical polar coordinates? It's very easy. I mean, if you have read about it, it's taught in our first year of like. I cannot see if there is a message. Just a minute. Okay, yeah. Thanks for writing down. Yeah, it all. That is how you describe it. So if you remove the infinitesimal d thing, it's like r square plus r square delta theta square plus r square sine square theta d phi square. That is how you describe distances in spherical polar coordinates. But then again, as I say it again, that it is still representing the same flat space. It is not at all representing anything else. You can describe it in Cartesian as well as in spherical polar. It's just that since we have changed the coordinate system, suddenly everything changes, right? Mishi, can you actually go back to the slide where we defined metric tensor for Minkowski? Oh, okay. Now, here, yeah, there's something more that I wanted to say that I did not. I don't remember if I did, so I just mentioned. So what we did here is while defining metric tensor, I said there are we have 4 coordinates, and I said that there could be cross terms as well. But how does metric tensor? How do we get a metric tensor? Metric tensor is simply the coefficient of all the terms that you see here. In this case, there are no coefficient. By the way, CDT is our coordinate. It's not T, first coordinate. So it is -1 and then 1, 1, 1. So that is why this is how a metric tensor looks like. All the diagonal components are -1, 1, 1, 1, and all the off diagonal components, which consists of all the cross terms, are 0. Now, my question to you is, if I'm writing this metric tensor for Minkowski, or Cartesian for 3D, if I'm describing it in polar coordinates, spherical polar coordinates, what will this be? Like, how will that metric tensor look like? It won't look the same, by the way. It will have some very, very small differences. Because if you see in the definition of ds square in terms of polar coordinates, it does have coefficients. Now CDT square is same, so first term will remain, the 0, 0 term will remain -1, but the 1, 1 term, will there be any changes in the 1, 1 term? The coordinates here are CDT, R, theta, and phi. Just answer in yes or no. What will change in the 1, 1 term? The 1, 1 term is the RR term or the coefficient of dr square. Should I expect a response? Are you guys still thinking? It's very simple. Just look at the definition of ds square that someone has written on your chat box if you do not know about it. But will anything change? As someone said, yeah, nothing will change because again, dr square has no coefficient. Now the next coordinate. Coming to the next coordinate, which is our theta, the 2 coordinate. Will it there be something else, or will it still be the one? Exactly, it will have r square. And then has someone raised their hands? I think someone has raised their hand. You can uh, Rohit, you can like allow them to speak if they want to.
Yes, I will.
Yeah, please, let them speak if they want. Have they been allowed?
Yes, he can speak.
Okay.
Sir, I can explain these topics.
Uh,
Sir,
which part? Which part?
it was the Minkowski dimension.
I had a bit of noise, so I could not really understand your question. But I'll try to explain the metric tensor again, because metric tensor is very important. By the way, this session might get extended a little bit. I'll try to explain the metric tensor again. So the metric tensor, how it works is there are four there are 4 rows and there are 4 columns. So the first why are there 4? Because we are using 4 terms to describe our space-time. We have CDT, X, Y, and Z. That is why there are 4 rows and 4 columns. So the very first term, the 0, 0 term, is actually describes the TT coordinate, or the DT square ka coefficient, CDT, C square DT square coefficient, which is -1 in this case. I'm talking about Minkowski for the moment to explain it. For ds square, yes. What about the 0, 1 term in this case? 0, 1 term actually describes if there were a coordinate something like c square c dt dx. If in the definition of ds square there was a term with c dt dx, then it would have gone in the 0, 1 term. Since there is no such term, its coefficient is 0. That is why the 0, 1 and the 1, 0 term is 0. The only non-zero terms are the diagonal terms, because the only terms present in the definition of ds square are dt square, dx square, dy square, and dz square, or the tt term, the xx term, the yy term, the zz term. There is no xt term, there's no yt term in the now definition of the line element, the Minkowski line element. That is why other terms are 0. So I hope you have understood it. If not, this is something very basic, and it's very important that you understand this. If not, we can stay after the session for some time and we can just I'll discuss about it more. But yeah, for now, now since I was telling you about ds square in case of spherical polar coordinates, so in that metric tensor, it has -1 in the first term, but 1 in the second term. But there will be, for the phi theta term and phi term, we will have a certain change. And as someone has mentioned, the TT term will have r square. Why will it have r square? Because in the definition of ds square in spherical polar coordinates, we defined d theta square. I mean, d theta square has a coefficient of r square. Similarly, d phi square has a coefficient of r square sine square theta. So we will have these terms present. So our metric tensor in case of a spherical polar coordinate for a flat spacetime will look like a diagonal matrix with the terms -1, 1, r square, and r square sine square theta. So I just wanted to show you this because that is how a metric tensor looks like. And in a general metric tensor, the other elements will also be non-zero. I want to mention something else as well here. Now, when you write line element, if I write if I add an additional, cross term like dx dy, for example, and if I write 2 terms, dx dy and dy dx, will there be any difference in these 2 terms? Can I write? Is it fair to write after dz square? Is it fair to write dx dy plus dy dx? Are these two different terms? Uh, yeah, I mean, I'm waiting for a response here. The cross term, like, yeah, if the ds square, if the definition of ds square had a dx dy and had a dy dx, are these two different terms? What do you guys think? Just mention whatever you think. It's okay to be wrong. It's good to be wrong. So, by yes, do you mean these two terms are different? dy dx and dx dy? Okay, I really like I mean, the way that you guys are really thinking about it. Uh, so when but then dy dx and dx dy, they are not different at all. They are the same terms. It's not just about being isotropic. It's about the definition of multiplication. It comes from something even more basic. It's not about isotropic. Even if you describe a non-isotropic space, even if you are describing a Kerr black hole is non-isotropic. But even in that case, like dx, dy and dy dx means because we are simply multiplying dx and dy, right? If you look at it in a matrix, that is when you see two different terms for x and xy term. There's a xy term and there's a yx term. But if you are multiplying, we don't notice any difference. The ultimate purpose of having a metric tensor is simply to have the coefficient of the two multiplicative terms. So what happens is this basic property of multiplication leads us to a very simple property of metric tensor itself. You know what that property is? It simply is a metric tensor is always symmetric. As simple as that. So here you see 0, 0, 0, so you don't really understand, but a metric tensor will always be symmetric. Or the metric tensor will only have 3D metric, like a 4D metric tensor will only have like how many 10 independent components. Yeah, that's what I wanted to just describe. Now we can, Amishi, we can go ahead to the FLRW metric. Oh yes, why is there -1? And someone was also asking me about. I just forgot that question. Thanks for reminding me about the signature being plus minus 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 or minus plus 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 plus. So the point is is by convention. Some books like to write it in plus minus 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 form, or some books like to write it in minus plus plus plus. The ultimate purpose is while defining ds, just have a change of sign. While defining ds square, it's about what you usually prefer. It is just how you choose your coordinate and how you choose to define it. Both of them are, completely correct. While I am teaching this, like the session which I am going through, I will describe it in minus plus 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 signature. Point is the time coordinate has a different signature than the spatial coordinate. That's it. Now coming to our FLRW metric, which is so this is the metric that we use in cosmology. Now, how do you get this metric? You do not get this metric by doing any calculation as such. Something very interesting. As we go ahead, we'll see the recipe of describing universe. But what happens is in a cosmology, when Robertson Walker was doing this, we start with the cosmological principle where we say that our universe is homogeneous and isotropic. Now, in order to describe a homogeneous and isotropic space, uh, write a metric for that. What will be a metric for that? What will be the metric for homogeneous and isotropic 4D space? Okay, we are losing out on time, so I really don't want to even answer directly. I want you guys to think, take your time and think. Oh, it's okay. We can give it some time. I mean, for homogeneous and okay, I'll just tell you the answer in this case. A homogeneous isotropic space is described by Minkowski, isn't it? Yes or no? Oh, you don't understand the question. My question was that what uh, ds square, what interval will you use to describe a homogeneous and isotropic space? So, like I said, it's described by Minkowski, isn't it? Someone has said yes. No, that's where you guys have to think. It is not. It is, yeah, metric. I understand. Metric is what we are looking at. This is what the metric usually means. Metric means how you measure distances. But the answer is not yes. It is not. Minkowski is not used to describe a homogeneous and isotropic space. I forgot to add one term to it, which is very important in describing Minkowski space. You know what that is? A flat space. It has to be flat as well in addition to being homogeneous and isotropic. So yes, keep that in mind. Huh. Yes. So as we move ahead now, what Friedman and Lemaitre and like all these guys did was they have their own contribution to the definition of this metric. They started with flat space time and how you see it is flat space. And now this is something that you would have like seen it just has some additional terms to it. Now they added curvature term to it because what happens is when you are describing curvature, you don't usually you cannot just stick with Minkowski. You have to add some additional term to take into account the curvature because it is not good to simply say that universe is flat. It could be curved as well. So that's why as if you can see the denominator of dr square is 1 minus kappa r square. Another interesting thing that I want to mention here is that the kappa here that you see, it is not same as the kappa that you saw before in the definition of curvature. Why is it not the same? It is the same only, but this kappa can take it does not only take values of -1, 0, and 1. It can take any value because this kappa is actually the kappa that you saw before divided by the radius of curvature. Is this clear? The definition of kappa. Uh, yes, okay. Now, however, there is one more term present in this. Okay, by the way, one more thing I want to mention. You see the sigma there, right? The capital sigma in this definition. So capital sigma is nothing but the uh, d theta square plus sine square theta d phi square. Why do we usually write it as sigma square? It is because since our universe is isotropic, it is independent of the angles that like we are in. So that is why we usually write it as d sigma square in many cases, as you would have seen in case of black hole as well. You can simply take d sigma to 0 and you do all the calculations for r square. You just see radial stuff because yeah, because of spherically symmetric case. It is a simple case, so that's why we write it as sigma. So don't get confused. The capital sigma, that's what it represents. Oh, wait, it's not sigma, it's omega, right? Sorry, I keep on saying it's sigma. The capital omega, I meant. I'm really, really sorry for that again. Yeah. And yeah, coming to that, but then you see an additional term apart from curvature and the capital omega that you are seeing here. There is one more term, the a squared t term. What is that? What is that accounting for? Why is that present? We have not looked at anything like that yet, isn't it? But this FLRW metric, it has something. Anyone? Yes. And as I see some responses, it is called as a scaling factor and it actually takes into account the expansion of the universe. Someone was asking me if for spherical space, the R part would be infinity. It would not be infinity because as you tend towards infinity, that is one thing, but kappa becomes automatically 0. So the weightage of kappa is, more than I mean, yeah, kappa becomes 0 or the radius of curvature becomes infinity. So when kappa becomes 0, the 1 is still there. So dr 1 minus kappa r square is not 0 for a flat space. 1 minus r kappa r square is 1 for flat space. So it simply becomes the Minkowski that you have seen, but then you have an additional term to it, which is a square t, which is the scale factor. Now, what does scale factor account for? Someone has said it accounts for expansion of the universe. Does it? What does scale factor actually mean? Yes. That's what kappa means. Yeah. Oh, okay. I want to clear something here. R square that you see here, 1 minus kappa r square, the small r is the coordinate r. It is not the radius of curvature r. Radius of curvature r is usually described by capital R. That is different. This small r is the coordinate r. When we are describing a point in space-time, we say no, r is equal to this, r theta is equal to this, phi is equal to this. So this r is actually the value of the coordinate r, not the radius of curvature. So 1 minus kappa r square would be like, yeah. Okay, that was a doubt. Yeah, sorry. So yeah, does A of t account for expansion of the universe? It is called scale factor because it not accounts for expansion of the universe. I mean, in a way it does. It not directly accounts for expansion of the universe. It actually accounts for what is expansion. We will actually see it in tomorrow's, like day after tomorrow's session. But it actually accounts for something interesting. When you know that universe is not stable, you know that distances are changing. So if distances are changing between 2 points, at one point, if I mean, you have to keep in that. I mean, keep that into account. If there was 5 centimeter distance between two objects at one point, it will expand and then that distance will become 10. So, but then coordinate systems also expands in that manner. So coordinates will still remain the same. You need to have something to account for something that has changed. That is why we introduce this A of t. And just keep in mind as this A of t that you are seeing right now is the most important term in cosmology. And that is the only term at some point that we will be looking at. So yes, this is a very important term. Just keep it in mind. You can move to the next slide. This is the FLRW metric, boys and girls. Just have this in back of your mind. Write it down somewhere because it will be used everywhere where you go. That is how we always start with, and that is what we have always used. You always start with a metric to describe a space-time. Something has asked a doubt. Someone to calculate distances. I don't understand what the question is. Is it a question? Okay, I don't understand the question. If you can type it in a proper manner, I'll answer it. Otherwise, I mean, if it's a long question or something like that, we can do it probably towards the end of the session. Okay, no question. Perfect. So while keeping in mind the FLRW metric, we have to go into a little bit more basic of why we are using the metric and why at one point I said something like something called as the difference about being space being curved or flat, or how we said about geodesic, and how it's not about the force, it's about the curvature of space-time. So where did it all start? I mean, people have not known this forever. It started at some point, and I'm pretty sure most of you know about it. But its story goes back, way in the past. How did it all start? How did this description start? We are doing cosmology. Cosmology is sort of an uh, part of astronomy. But how do we explain the physics of cosmology? The space and everything, even the metric itself. Why do we define a metric? What is the use of a metric, and is metric only to show you how different things are, and how do you use metric to do different calculations, and what else does a metric show? Is the metric just there to describe a coordinate system, or does it show something very inherent to space-time, something that is not about the coordinate system only, something which is about the property of space-time itself? For everything to learn, we will go through everything. We need to know about how did it all start. It all started actually in 1687 with the Apple story that we all know about. I'm not sure if that story is true, and in most probably it is not true. But yeah, I mean it's a good way to tell a story because it's always easier. In 1600s, Sir Isaac Newton gave us our universal law of gravitation, which I hope you all remember. By the way, just because you're studying cosmology, it does not mean that you forget the Newton's gravitational law. It is not that Newton's gravitational law is wrong. Newton's gravitational law is right, and it works for a lot of systems even today. The all the current theory about gravity that we have is just a minor modification to the Newton's gravitational law. That this is still the 1/r² law is still valid to some extent. So yeah, every one of you should know this law very well. But then, yeah, in 1798, Henry Cavendish determined the value of gravitational constant. Newton just said about the proportionality, how it is directly proportional to the product of their masses and inversely proportional to the square of distances between them. But it was Cavendish who determined the value of that constant. And till here, you all know very well about, right? But then something magical happened in 1905. And the magic which was meant to change our world completely. So was it? There was a young German physicist. He was not even a physicist at that point. He did have a degree, but yes, he was a Swiss patent clerk at that point, but still a German. And then he produced 4 papers. The 4 papers which changed the world completely. And the point is, all these 4 papers were very, very different from each other, but they're very important. It's not possible to, it's not fair or even possible to study cosmology without using the word Einstein. And you will see later on why. It was young Albert Einstein who publishes his 4 papers, and one of the papers, which makes no sense at that point, is the paper on special theory of relativity. Was Einstein the first one to mention Minkowski, mention how light moves and mention everything? No, not at all. There's a reason why it is called as Minkowski. Why we use something called as Lorentz transformation in special relativity, because it was already known before that. Now then, what did Einstein do? What Einstein did was Einstein just told all the theory that we had, the Lorentz transformation was already present. All these Minkowski line element was already present. Einstein simply said that this is how the real world works. It is one thing to create a physical construct, a physical theory, and it is completely another thing to say that to explain how a particular theory describes the actual world you are living in. So this is where the young Albert Einstein comes in. This is what happens in 1905. How he describes, the space and whatever we saw. There are only 2 postulates of special relativity, which is, do you guys know about 2 postulates? Just answer in yes and no. No need to type the entire postulate. Just answer in yes and no. That is all special relativity is, just those 2 postulates. And the rest, whatever you do, the length contraction, time dilation, they are just a result of, whatever happens. Like those 2 postulates. The 2 postulates, yeah, I mean, I'm glad that at least some people know, but I'll just still tell it to people who do not know. The 2 postulates of special relativity are: first, the speed of light in vacuum is a constant. And yeah, I think it's constant, or is it the fastest? Oh, even I forgot. Those are some things you see, these things, these laws are very, very, very basic. It's very, very, easy to just do your physics and everything without just remembering, but it's very important to keep that in mind. So, yeah. And okay, it's the speed of light is constant. That was a postulate which was sort of known, but was not really accepted, because the constancy of speed of light actually contradicted the ideas of classical physics that we knew till that point. So it was actually this particular postulate which actually blew people's mind. Because if the speed of light is constant, then time is no longer, universal for everyone. It has to be personal, which change everything and which actually introduce the ideas of time dilation and everything. So when I said that when I am speaking to you, you're not listening to it instantly. That is because of constancy of speed of light. Secondly, when I say that the idea of simultaneity is lost, two events can be simultaneous for me, but might not be simultaneous for you, is also a result of the constancy of speed of light. So yes, I mean, I'm not going to go deep into it because we are not here to cover special relativity. Our purpose is something else. And then the second law, or the first postulate was the laws of physics are same in all frames of reference. All frames of reference moving with constant speed. This is also very important. This simply tells you, what does this imply? The statement is the laws of physics are same in all frames of reference moving with a constant velocity, but it has an implication which is more important. It simply implies that no frame of reference is special. Do you now get where the term special theory of relativity comes from? Theory of relativity is not given by Albert Einstein. It was given by Galileo, Galilean relativity, way before in 1600s itself. But Einstein's theory is called special theory of relativity. That is where the special comes from. Ironically, it just removes the idea of there being a special frame of reference. So if we have understood this, we will move ahead now. Just a minute. Yeah. So after this 1905 paper, it was about special relativity. But then, there's something very interesting. My point is, you do not live in a world where all the frames of reference are, moving at constant speed with each other, right? There are forces. Forces affect. There's acceleration and everything. And special theory of relativity gave no account for anything of that sort. What happens in a general case. So what Einstein did in 1907 was he introduced equivalence principle. Have you heard of equivalence principle? The equality of inertial mass and the gravitational mass. This is where his focus shifted more towards what happens in what exactly is gravity. Now it is difficult to describe gravity was because what is the goal of the physics in general? The goal of physics in general is to describe the ultimate goal of physics is to unify all the four forces and give one single theory of everything. So in that, the first thing is to unify all the forces and then just mention that all these forces are just different aspects of the same thing. Guys, it's close to 1 p.m. now. The supposed time when we are supposed to end the session, but I'll extend it a little bit. I'm like talking about stuff which are not exactly a part of this syllabus that we are covering, but then I think which is something important and something interesting as well. So our goal of physics is to understand the cause of everything, and to understand the cause of everything is to describe that it is there's one theory which can explain everything. And the first thing to explain everything is to explain all the forces. Because if you explain all the forces, you have explained everything. Because whatever's happening, whatever happens in real life, it is because of the forces. We have four fundamental forces. Now the problem is we have easily unified the three fundamental forces, the electromagnetic force, the strong force, and the weak force, but still we could not unify gravity. We have not done it till now. There have been lots of theories about it, but we have not. So just because we could not unify gravity, it is very obvious thing to think about, right? Is gravity something else? Does gravity mean something different than what we know it is? So that's what even Einstein was thinking all this while. And that is when, furthermore, he predicts gravitational redshifts and all that stuff. But what he does is, in general theory of relativity, he finds out, or he says that gravity is not a force at all in the classical sense of what force means. It is not like, like it is not like how you study an electromagnetic force with an electromagnetic field, or, like photons or other things. Gravity is simply, an effect of your space-time being curved or being in a particular shape. What I want to say here is, It is simply the go back to the example which I said, where you are walking on a road which is actually curved. And by the way, you are confined to walk on a road only. Just assume that you cannot walk anywhere else. Now, this does not make sense in roads example, but that's how space time works. There's nothing, we do not know what exists beyond space. So space is where we are. So we have to move just how our space moves. So now think about a road, a curved road. Even if no force is acting on it on that road, you still walk on the road, right? If it is curved, you have to move in a curved shape. Now assume someone who is looking at you from a distance, and someone who cannot see the road, and they just see you, you are walking in a curved space. I mean, you're turning. So if you're turning, you are accelerating. If you're accelerating, some force must be acting. So the person, like at that distance, it sees that some force is acting on you, which is making you turn. But then for you, you're turning because this other space is no force is acting on you, right? That is what is equivalence principle means. And this equivalence principle is actually the basis of general theory of relativity. I mean, there's a lot more to it, but that's the basics of it. So did you guys understand what equivalence principle actually means? It simply means that gravity is not a real force. What we perceive as gravity, what we call as gravity, is simply us seeing that an object is. It seems that a force is acting on an object because space-time is curved in that particular place, and that is why the object is moving in a certain way, making us feel that there's gravity all along. For example, if someone is depressed in IITM and commits, okay, this went dark. Never mind. For example, if some let's take an example of an elevator. Yeah, forget about the example that I was giving before. Consider someone falling in an elevator. So one might feel that you are falling because of gravity, because Earth is attracting you. And what Einstein said was, it is not because Earth is attracting you. It is because the space near Earth is curved in such a way that that is how you move. That is what your geodesic is. So yes. Then moving on to the year 1911's prediction. I might get cancelled for the example that I was giving, so please let's forget about it. But yeah, I mean, again, that's the truth. So yes. Einstein, how he does it, he predicts something called as gravitational redshift and bending of light by gravity. How he does that, we will look into it later on. But then, yeah, that is how he predicts something. There is no proof of it yet. What does he predict? He predicts that, you know, okay, Newton said that gravitational is the force which is acted upon by a mass, right? So how do we account for mass? We just said that the space-time is curved. So Einstein said that the presence of any matter curves the space-time, and it is the curved space-time that causes an effect for smaller objects moving around it, which seems like gravity. And then again in 1915, he represents the field equations which actually describe the general relativity. Now, the entire theory of general relativity is actually mentioned, is actually specified in just two sentences, two very famous sentences, which I want you to listen to it very, very, very clearly. I'm assuming my voice now, because these two are very important sentences, and this will cover everything that you need to know in general relativity. Just two sentences. In fact, it's one sentence, one compound sentence, which can be split into two parts. So listen to it carefully. General relativity of theory says that matter tells the space-time how to curve. That's the first part of the sentence. And the space-time tells matter how to move. That's the second part of the sentence. That's it. That is your entire GR. Now, what does this mean? You can go deep and deep into it. It means that matter tells space-time how to curve, or the presence of matter causes a curvature in space-time. It is simply the example that we see of a ball being thrown on a sheet. If you throw a ball on a sheet, it just curves, which is the example which is very commonly given. And then if the sheet is already curved, an object around it will move in a particular way, and it will seem like it is the gravity that is causing that object to move in that particular way. That is all. That is all general relativity is, and that is all it says. How right it is, and all the things that happen at cosmological, at quantum scales is a different debate altogether. Yeah, we'll not go into it. We have already exceeded our time, so yes. You can move to the next slide, Anishi. Yes. So what happened in 1916? our very famous Karl Schwarzschild, after which we have named the Schwarzschild metric. He provides the first exact solution of Einstein's field equations. What are the solutions, by the way? Do you guys know the solution? The first solution of Einstein's field equation. Again, this is something that you learned about in your last week's session. Not the black holes. Einstein's the GR has nothing to do with the object present there. That comes into the domain of astrophysics. It has to do with genetic property of a space-time. So yes, it is a Schwarzschild metric. Schwarzschild metric is not necessarily for black holes. In fact, black holes cannot be described by Schwarzschild metric completely, as you saw in that session. You need to have additional coordinates. No, it's not the expansion of the universe. That's not what Schwarzschild did. Einstein's solution was not for the universe. It was just by the way, GR and cosmology are not the same thing. GR is used to do cosmology, but GR is simply a theory that can be and that is applicable everywhere. A theory should be applicable everywhere. The more valid a theory is, the more, the better it is. So Schwarzschild gave a Schwarzschild metric. Schwarzschild metric simply defines how space-time works in a spherically symmetric, in vicinity of a spherically symmetric mass distribution, which you saw in the last example. And then 1919, Arthur Eddington did something which we will see later on, how he confirmed actually the presence of the rightness of general relativity. And then in 1922, Alexander Friedmann, the same one after which we will study about something called as Friedmann's equations, he started doing some dynamics and some solution to see again, as I said, Einstein's field equations are theoretical equations which can describe anything. And now you apply these field equations, which are differential equations, to various parts of universe, and then you see what the solutions give. As Schwarzschild solution gave us the Schwarzschild metric, or how a metric describes the space-time. So it gave us how the space-time is. Alexander Friedmann's the solution, which gave us the FLRW metric on the Friedmann equation, suggested that the universe could be expanding. And then the Lemaitre, another guy whose name is present in our definition of FLRW, what he did was he independently proposed an idea of expanding universe, the Big Bang theory. And again, moving on to 1931, when Einstein himself acknowledges, by the way, Einstein as a person is a very stubborn person. He believes on something and he's very hesitant to think about something else. I would call him conservative in that way. But yeah, was very difficult for him to explain the idea of an expanding universe, to think that universe could be expanding and universe could not be stationary. So he added a cosmological constant. We'll see what cosmological constant is and what it did. But then again, he was very hesitant and then he put it to 0 and things like that happened a lot. When was the point when Einstein actually agreed to there being an expanding universe? A scientist never believes something unless he sees or observes it. So can someone mention not the year, but a specific event that might have happened in our history that made him and everyone else believe that universe might be expanding? Very famous observation. Yeah, as someone is saying, yeah, it was Hubble's discovery. What was Hubble's discovery? That again, we will see in the next session. But yeah, for now, yes. And then Jocelyn Bell Burnell and Anthony Lewis, they discovered pulsars. Pulsars is a different story altogether, which we will not cover in this session, but we can discuss about it at some point. I've written an interesting article about actually Jocelyn Bell's discovery of pulsars, something very irrelevant to our session. Just see what it is. And you will move to the next slide. Now we start doing the actual mathematics, moving on from the history. I've mentioned about Einstein's field equations. The field equations actually describe our general relativity. How? I have said that matter curves spacetime, but how does it do? How does this happen? is what is given by Einstein's field equations. As you see right now, we have G mu nu is equal to 8 pi G by C k power 4 by T mu nu. Now, again, this term that you said has lots of terms in it, lots of terms that you might not have seen before. So I'll go through these terms one by one, very slowly. And this is the last topic, and this is where we will end our today's session. So on the LHS, you see something called as an Einstein tensor. What does the Einstein tensor describe? An Einstein tensor describes the property or the space-time itself. What it does and how it does, we will see in next slides. But for now, you can assume, you can just simply understand Einstein tensor is something which describes the space-time itself. Got it? And then on the RHS, you see a T mu nu. T mu nu is called a stress energy tensor. What does stress energy tensor describe? Stress energy tensor describes the properties of the mass which is present. When we say that matter or mass curves space-time, so how do we describe matter? In GR, we describe matter using its stress energy tensor. Stress energy tensor is also, if you're working in 4D space, stress energy tensor is also 4-dimensional metric, just like a metric tensor that you saw. And yeah, both mu and nu go from 0 to 1. Sorry, 0 to 3, 0, 1, 2, 3, and 0, 1, 2, 3. So it is very similar to what the metric tensor that you like that you saw before. And people asking about feedback form, don't worry, you will get feedback form by the end of the session. And you can write all your frustrations in it. I understand that. Yeah. Yeah, let's just finish with this though. The T mu nu and the G mu nu, the stress energy tensor, you might not understand it now, but just listen to what I am saying and try to listen if you understand it well. If you not, it's okay. The first, row and the first column of T mu nu, it actually describes the energy density, and the rest of the 3x3 matrix, the remaining 3x3 matrix, thing, the pressure. So we have energy density and we have pressure or momentum, whatever you want to call it. It's all interconvertible in relativity, by the way. If you read study of relativity, you will study that. So on the LHS, we have something that describes how the metric curves, and on the RHS, we have something that describes the presence of matter. So this is how it says that these two are proportional. That is how we represent our definition of how matter curves space-time. And what about 8 pi G by C k power 4? These are constant. G is the Newton's gravitational constant that we read about, or in the previous session, like in the last week's session, they might have told you about Einstein's constant K. This is what Einstein's constant, the 8 pi G by C k power 4 is Einstein's constant. This is what it means. How it comes, the proof of it, it is actually provable. It is proved, but yeah, you have to do like your entire GR course for it. And for cosmology, the proof is not important. Just the acceptance that it exists. It exists is fine. It is not difficult, to be honest. It is very logical. The flow is very logical, but it is possible. It is a bit difficult to explain it, in 1 hour or in some time. If someone has time, one can go about explaining it. There can be a session on GR itself, and people will understand it very easily. So I'll say it's not difficult, yeah, but it is involved. It's not simply, maths can never be done simply by looking at equations. You have to take a pen and paper in your hand and start solving it on your own. But yeah, let's not go into it. Let's now T mu nu is very clear what it means. It is a stress energy tensor. But G mu nu, Einstein tensor, I've just said that it describes space time. I have not said anything more. All you know at this point about space time is metric tensor, isn't it? You know nothing else. Okay, I want yes or no quickly now, because we might not spend much time. So all we know about space time till this point is metric tensor, which was described in Minkowski as eta alpha beta, or like which will be described as small g mu nu. The capital G mu nu is Einstein tensor, which is something different from how do we convert from small to capital? Like how do we reach there? What property of space-time does capital G mu nu or the Einstein tensor describe, which is which actually helps us reach the metric tensor? You can move to the next slide, Amishi. Now this is what Einstein tensor describes. Now from this point, you are going to see a lot more tensors, a lot more terms. There are a lot more terms, but then we have to go through it one by one in order to understand what how do we, reach the metric tensor? And in the end, it will all start making sense. Now it might seem a lot. You can note it down if you want, but you can choose not to. It's up to you. A metric tensor is defined in this way: Rij minus 1 by 2 Gij R. Now, when I write Ij, please understand that these I and J, it takes value from 0 to 3, both I and J. So 0, 0, 1, 1, just like, in a vector, we sometimes write it is as, a vector R as R of I, Ri, Rx, Ry, Rz. So Ij here, they are like Tx, Y, Z, if you want to talk about Cartesian. But since it's better to stay independent of coordinate system, we call it in terms of numbers, the 0th component, 1, 2, and 3 component. So this Rij is something called as a Ricci tensor. And the R that you are seeing here, it is not the radius of curvature that we saw before. It is called as something called as a Ricci scalar. Now, what are these Ricci scalar and Ricci tensor? The definition of Ricci scalar and Ricci tensor is, you can see here, it is defined by another tensor, which is even bigger. It has K. If you see, do you see the another tensor? It has like 4 terms. I mean, you can get Ricci scalar just by multiplying. One more thing. So in the definition of Ricci scalar, you see Gij. Gij is the metric tensor. There we mentioned it for Minkowski. We mentioned it using eta symbol, and it is only for Minkowski. But in order to represent a general metric tensor, we use G instead of the small g instead of eta. So wherever you see small g, we are talking about a general metric tensor. It can be of any form. It can have anything. It is not the diagonal of -1, 1, 1, 1. Okay? I mean, yeah. So, and how do you obtain Ricci scalar? You multiply Gij with Rij, and then you obtain one single quantity, which is known as Ricci scalar. Now, Rij, Ricci tensor, is where you learn a new term. Does anyone know what this term is? Tensor with 4 components. Yes, as someone said it, it is called as the Riemann curvature tensor. And it is the single most important tensor that is used to describe your space-time. Let's not call it just Riemann tensor. It's called as the Riemann curvature tensor. How do we obtain from Riemann to Ricci? We simply, if you see, the 2 indices are same in this case. So do you know, if we write it, if we repeat one index, it gets added. You might have studied it in your physics 101. Like Vij is, I and j goes from 0 to 1, a general vector or a general tensor. But if I write VII, it means V11 plus V22 plus V33. So what we do here is that Riemann has 4 indices, we make 2 indices same, or we sum over it. So we just have 2 independent indices. So yeah, that's how we get from Riemann to A. Now, what is Riemann? Riemann is single most important. You can move to the next slide. I hope this is clear to everyone, the definitions at least. Please keep on asking doubts if there. Now the Riemann curvature tensor. Here you are seeing, yes, something else, something even more interesting. I mean, I know there you are seeing a lot more terms. I will define all these terms for you in a simple manner. For now, you can note it down. But in order to understand it deeply, you need to do a GR course. It's not possible to really do it in a session, but it's just good to know at this point. Riemann curvature tensor, what it does is it describes the curvature. How do you describe okay, I have a simple question. You have an equation, a simple mathematics question. You have a simple equation, y is equal to mx plus c. No, mx plus c is very simple. You have y is equal to, let's say, ax square plus bx plus c. It describes a curve, right? But how do you describe the curve's curvature? I mean, you cannot tell anything using the equation itself, right? You have to take its derivative. Now you take its first derivative. What do you get? After taking its first derivative, all you get is a slope. But can you still tell that is it like positively curved or negatively curved? What our purpose here is, when we talk about field equation, we are saying that matter curves space-time. So what we are interested in is the curvature of a space-time. So we need something that can describe curvature. As someone has said this, we cannot describe curvature using first derivative of any equation. We need second derivative. It is exactly the same thing that we are doing. We have our metric tensor, but our metric tensor is not enough. It just metric tensor just tells you, how do you find distances and how does your if I had to draw a mathematical analogy to it, it simply tells you how your equation looks like. As simple as that. Nothing else. But in order to describe curvature, you need a second derivative. And that is what is Riemann tensor does it. But it is not very simple. You cannot simply take a second derivative of it. There are ways to it, how you take a second derivative. In this case, that's how it is defined. So here you can see a new term. It is a capital gamma actually, and it has 3 indices. So does anyone know what these are called? I mean, I won't expect you to know. It's okay. It's something very new for everyone. But before that, it's good that if someone knows. Before that, if you can see that since it has 4 components, like 4 indices, the Riemann curvature tensor, one can say that it will have how many total components? It will have 4 into 4 into 4 into 4. Since every term goes from 0 to 3 or can take 4 values, total number of components in Riemann curvature tensor is 4 raised to 4, which is 16 ka square, 256. I think it is 256 is the right answer, but yeah. But again, as we saw in, but now we are obtaining Riemann curvature tensor from our this thing, metric tensor. We saw metric tensor is symmetric. So not every element of metric tensor, is independent. There are only 10 independent components of a metric tensor. So if you move from there to Riemann, all the 256 components are not independent. In fact, very few components of Riemann are independent. Here we are talking about n-dimensional, 4-dimensional of space. So in case of n-dimensional space, it can be anything. Because when we talk about GR stuff, we don't usually talk about our universe as such. We talk about some things which are very general. So it is described by n into n square minus 1. Get it very simply by doing PNC. It's a very simple permutation and combination problem. How you get n into n square minus 1 by 12. So n into n minus 1 into n plus 1 wala formula. And as someone has said, these gammas are called as Christoffel symbols. What does Christoffel symbols do? You can move to the next slide. Amish, you can move to the next slide. What Christoffel symbols do is that, so as you see, we see derivatives of gammas here, derivatives of Christoffel symbols here. Since it is a second derivative, Christoffel symbols itself describe first derivative of the metric tensor itself. Yeah, yes, Aniket, how tensors change in parallel transport. Yes, that's what it describes exactly. So, but then how it's for explaining that we need to explain what parallel transport means, and I don't really want to get into that for now because we need to have a lot more explanation in order to describe Christoffel symbols, in order to describe parallel transport. But just assume parallel transport simply means not changing vector curve. So how does it change? And or in a very naive definition, or you can say it takes in account the first derivative of metric tensor itself, and that is how it is defined. Also, an additional thing you might see in certain cases, I have written Gij as lower indices, and in some cases I've written it as upper indices, and no one has asked me yet the difference between these two. So I'm a little bit surprised that you guys have not noticed it. But since you have not asked me this, I am not going to tell you this. You have to ask me questions in order to get answers. A very simple, thing about science. You know the right questions to ask. Moving along. So this is what we know for now, Christoffel symbols and all this. And you can go to the next slide. Sure, what's there in the next slide? Yes, someone has asked me what is parallel transport. Parallel transport in a general way means if you take a vector and if you transport it parallelly, as in if you transport it in such a way that its magnitude does not change. That is what parallel transport means. So like in case of a flat space, it simply means that take a vector, assume a vector to be an arrow, and transport this perpendicularly. It won't change. It is just moving along a straight curve. That is what parallel transport means. But then the definition gets a bit more general because heads geodesics are not necessarily straight, they are curved. In curves, there is a chance that vectors can change. So there's a way to describe it. Yeah, we are transporting it parallel. It's very simple. You just assume there's an arrow which is kept on your table. You lift it up and you keep it somewhere else without changing anything. And yes, since direction and magnitude are both properties of a vector, you have to keep both of them same. Yeah, anyways. So now since we have seen all the tensors and vectors that we have, we will go on to describe what a metric tensor for this thing for the FLRW metric looks like. Because for us, FLRW metric is the most important metric. And this is how our FLRW metric looks like. It's very similar. It does not have any off-diagonal components. All the diagonal components are like -1. And since we had a square by 1 minus kappa r square, a square r square, a square r square sine square theta, this is how it looks like. And I don't think I need to explain it to you. I've explained it to you enough what metric tensors is supposed to be. And given the way you have looked at FLRW metric, you can easily understand what this is. And this is the metric tensor that we end of the day, that is what we need. I hope till this point, everyone is clear about all the tensors that we looked at. At least whatever I said, there is more depth to it, but we are not going there today. Is it? Okay. And now you can move to the next slide now. Now here we will see the recipe of, like, we have all these tensors, we have everything, but like, how do we work towards it? Like, what exactly do we do and how do we explain stuff? How do we use it? So what we do is we take metric tensor. We from metric tensor, we find out the Christoffel connections. So now, once we have the Christoffel connections, we find the Riemann curvature tensor. We use Riemann curvature tensor to find Ricci-scalar and Ricci tensor, and that Ricci-scalar and Ricci tensor is something we use to find Einstein tensor. This Einstein tensor is actually used to describe your space-time. But there's something interesting which I want to actually mention here. If you say that matter describes space-time, how to curve, shouldn't you start with actually matter and then move towards space-time? As in, there should be matter at present first, then matter should have their property and it should curve space-time in a way which should tell you the metric. Shouldn't it be the other way around? Other way around as in that you see going from a metric tensor to Einstein's tensor, but shouldn't it be like starting from Einstein's tensor, because general theory of relativity is a more basic theory. You start from that theory gives you Einstein tensor, and then you reach towards metric tensor. So in reality, this is how it is supposed to be. I don't know if you understood my question. Sorry, if you understood the doubt that I was trying to, like, put in your mind. But we start from general theory of relativity actually. So in that we have an object. So just go with me. Just hear me out what I am saying. Object in space-time. Imagine an empty space. We put an object in it. That object has a mass, has some properties. If something has some property, what will we use to describe that object? What tensor will we use? Anyone, quickly, come on. Here we have an empty space-time. No, actually, that's not how we do it. We have an empty space-time, and we have an object in it. We have something to describe an object. That object is described by something. What is it? Yes, it is the stress energy tensor, right? We have that stress energy tensor T mu nu. From the stress energy tensor, we apply Einstein's field equation. Einstein's field equation gives you this thing, the G mu nu or the Einstein tensor, and then we move back from it to find out what the metric tensor is look like. I mean, what does it look like? Now, but how do we do it in real life when we are doing calculations? Actually, is we sort of already have metric in our mind, and we just we describe a form of metric, assuming that if we assume the space-time to be homogeneous and isotropic, we write a metric in general terms, and then we use Einstein's tensor to determine all the constants that we had, like the curvature was a constant, was a parameter with the in the FLRW metric, the scale factor that you saw was a parameter. So we sort of define metric tensor to start with, and then we use the Einstein's equation, the field equation, to find those parameters that we have described. That's what it is. That is what general theory of relativity is all about. And I see someone is worried about attendance and stuff. I just want to mention that you don't need to worry about it. Attendance is automatically recorded. It will be shared on time. If you're worried about feedback form, it will also be shared. I mean, it's there in the final slide of it. You will have enough time to it. So just chill and focus on the session, please. Yeah. And coming to there's one thing that I want to mention. Don't stress a lot on your attendance or the certificates that you're going to get. I think it's much more interesting what we are trying to learn here than your attendance or the certificates and stuff. I don't know how much these certificates will help you in future, but the things that you learn here are going to help you a lot. I'll be very honest about it. Yes, so this is what the GR is entirely about. I hope that at this point you have understood, I mean, at least at the surface level, what we do in GR. If GR is very clear, that is when we can move ahead and start discussing cosmology. And this is actually where we will stop today. We have another session where we will go into more stuff about cosmology. We have one more slide. Amishi, can you move to the next slide? Where it is actually important. Once we have done the general theory of relativity, I mentioned about something in the beginning. It was just a minute. I am audible, right? Okay. Yes, I mentioned something in the very beginning, something about, you can give Einstein gave a theory of relativity, but then was general theory of relativity, but that theory was even more difficult to comprehend, even more difficult to understand. Because SR still it's fine, but GR, how will you even understand it? Like you are simply saying that someone initially has Newton has said that there exists a force. Now you are saying that there is no force. It's just how space-time curves. What does it even mean by curvature of space-time? All till now we have assumed that the space-time is flat. Curvature is not something that has even crossed our minds. So it's not very easy for scientific community to accept something of that sort. What you need to do is you need to show it in real life that whatever you are saying is real, and it's not some bullshit that you are speaking. And while Einstein was very much, persistent on what he was saying was right, it was a bit difficult for him to describe it because we needed an cosmological event to happen in order to show that whatever he's saying is right. How will you even show that space is curved? At that point, I mean, you have seen your first black hole now, recently. You have seen your first gravitational wave in 2015. At that point, 1900s, how will someone, accept GR? Because you have not shown them anything. You've just created a theory. Now I can create a random theory and I can say that is how universe works. But then is my theory is as good as the observations that I see. So this is what happened. When an ironical journey took place, Arthur Eddington was actually not a supporter of Einstein. He was actually someone who opposed Einstein and opposed the theory of relativity. What he did was he set out on a journey to actually not to disprove that relativity is right. He was a well believer that relativity is wrong, and what he did was, as we saw that presence of a heavy matter curves space-time, so we need to see what is the heavy matter present like very close to us. It is our sun, right? The heaviest matter present. So since sun is like such a heavy matter, it will curve space-time to a certain extent. And now, if we could somehow, if Einstein could somehow show everyone if that space-time around sun is curved, he would have proven it. But how will you show? I mean, in the morning when sun is out, you cannot see anything around sun. You cannot even directly look at sun. So the only way to see sun was during an eclipse. So this is what happened when Eddington went out on a journey. I think he went to Africa, where total solar eclipse was taking place. And that was the only point when one could actually, he could actually disprove that anything like this thing, curvature of space-time happens. And guess what? He set out on a sail on such a long journey to disprove Einstein, and he ended up proving him. That was the first proof that GR called as sensing. But yeah, it is a proof that space-time is not curved. I mean, sorry, it is a proof that space-time is curved around sun, or it was the proof that general relativity is right. So yeah, you can move to the last slide now. And yeah, people who are getting worried about feedback form and everything else, yeah, feel free. Meanwhile, I'll just like to end this session. This is where we end today's session. I'll just like to end the session by telling you that first thing, in today's session, we have covered the basics of cosmology, or the basics that we need to study cosmology. We have not really studied cosmology apart from studying the FLRW metric. But then we need these tools to actually study what space means. The name of our session was expanding universe, but we have not yet said anything about how universe expands and what does expansion means. What does even scale factor mean? So, uh, but basics, I hope you have, like, basics have been clear for you guys. I tried my best. And again, at the end of it all, I would like to apologize for all the technical issues that was happening in beginning. I know how frustrating it is to trying to learn something, and your voice is not even reaching there. So my bad. I'm really, really sorry about it. But I still hope that whatever I taught you, you guys understood it well. If not, I'm like open to you guys asking doubts right now, or like maybe you guys can ask right now, or if you guys want, you can stay around after session. I'll hang around for a while, or you can just contact any one of us. I hope our contacts are shared, and you can contact me as well. We can talk, and I really, really want to. I really find it interesting to discuss about all these things, everything that has happened and that will happen in the upcoming session. I mean, the best thing is to ask doubts right now. But yeah, I think Rohit, you can stop recording. And okay, now since the recording has been